Welcome to the introduction lesson on waves. Remember, you can skip back at any point or pause the video to help complete your notes. All the waves we look at in this topic are progressive waves. Progressive waves are waves that transfer energy without transferring matter. We'll look at an example of this in a minute. Waves fall into two main categories: transverse waves and longitudinal waves. Let's have a look at the difference between transverse and longitudinal waves. Here we have a line of particles. Let's see how a transverse wave moves. What we can see is the energy of the wave is moving from left to right across the screen. But the motion of each individual particle is only ever up or down. We call this motion the vibration of the particles. For this longitudinal wave, the energy has also been transferred from left to right across the screen. However, the particles here are moving from left to right. In both cases, the particles don't change position along the line. It's only the energy that's being transferred. This is why we say that a progressive wave transfers energy without transferring matter. In both cases, the energy transfers in the same direction. However, for a transverse wave, the vibration of the particles is up and down, and for a longitudinal wave, the vibration of the particles is left and right. We can use these observations to define a transverse and longitudinal wave. A transverse wave is one in which the vibration of the particles is perpendicular to the direction of energy transfer. And for a longitudinal wave, the vibration of the particles is parallel to the direction of energy transfer. Let's look at some examples. Waves on a rope, water surface waves, seismic S waves, which are the secondary waves when there's an earthquake, and electromagnetic waves are all transverse waves. Sound, including ultrasound, which is higher than human hearing, and infrasound, which is lower than human hearing, and seismic P waves, which are the first waves to arrive after an earthquake, are all examples of longitudinal waves. Waves on a rope, seismic S and P waves, sound waves including ultrasound and infrasound, and water surface wave all have something else in common. They're all mechanical waves. This means they require a medium to travel through. For waves on a rope, the medium is the rope. For seismic S and P waves, it's the ground. Sound, ultrasound and infrasound can all move through many different mediums. But in the examples here, the speaker is producing sound that moves through the air. The ultrasound of a fetus is moving through human tissue. And infrasound created by a whale is moving through water. Water surface waves also move through water. Mechanical waves cannot travel in a vacuum. Unlike the electromagnetic waves. This is the electromagnetic spectrum. It's made up of all of these types of waves: radio waves, microwaves, infrared, visible light, ultraviolet, X-ray and gamma ray. This is our spectrum. And at the top of the spectrum we have the lowest frequency waves and the lowest energy waves with the longest wavelength. At the bottom of the spectrum we have the highest frequency waves with the highest energy and the shortest wavelengths. Electromagnetic waves don't need a material to travel through, and they can travel in a vacuum. All of the waves on the electromagnetic spectrum travel at 3 × 10⁸ meters per second in a vacuum. We often represent waves on graphs. There are two main graphs you need to know about: a displacement time graph and a displacement distance graph. A displacement time graph shows how far away a particle is from the equilibrium position at any given time. If we look at a point on one wave to the same point on the next wave, the time between these points is known as the time period. It's the time taken to complete one full cycle. The amplitude is shown here. It's the maximum displacement from the equilibrium position. On a displacement distance graph, we're seeing how far away any particle is from the equilibrium position along the length of the wave. If we look at a point on one wave to the same point on the next wave, this is known as the wavelength. The amplitude, again shown here, is the maximum displacement from the equilibrium position. Here are some definitions you need to know. The distance between a point on a wave and the same point on the next wave is known as the wavelength. The distance and direction from the equilibrium position is the displacement. The maximum displacement from the equilibrium is known as the amplitude. The time taken to complete one full cycle is the time period, and the number of full cycles per second is the frequency. Finally, we need to look at the wave equation, which states that v equals f lambda, where v is the wave speed in meters per second, f is the frequency in hertz, and lambda is the wavelength in meters. Have a go at the questions in your book using this equation. Thanks for watching. For more videos, follow the link in the description.